The last time we tested nuclear weapons in this country was in 1992. So that was 28 years ago. And can you imagine if you had an airplane, say a Boeing 747, that hadn't flown in that amount of time? And you filled it with passengers, and then you said, we're going to fly it now. You need to be really certain that every component of that plane is going to work, and then when you put them all together, that they will work in unison. And that's the type of challenge that we face when we try to ensure that the nuclear weapons are going to work as we believe they should work.
We have been in the U.S. in a state for the past couple of decades where the stockpile was relatively static, but that environment is changing because of the developments in the international scene and because we are modernizing an aging stockpile. And so those scientific challenges, being able to underwrite them, being able to apply state-of-the-art material in nuclear science to stockpile problems, those challenges are growing significantly.
The distance between what we know about how materials behave, how nuclear fission works, neutron capture works, and where we need to be to truly understand how a nuclear weapon performs and can say with certainty that it will perform when we need it to, is huge. And so there's just an enormous amount of work that needs to get done.
Los Alamos, we have the integration between the materials manufacturing, we have the design portion, and then we have a number of test facilities from LANSCE to other facilities where we can test explosively. It's kind of a co-design capability that is resident at the laboratory.
Our mission here at LANSCE is to ensure that the U.S. has a reliable nuclear deterrent. And we do that work here because we have a powerful linear accelerator that is capable of doing experiments in nuclear physics, material science, high explosive science, and doing these experiments all at the same time. These protons from this accelerator feed 16 different flight paths that are simultaneously running 16 different types of experiments.
Materials are absolutely fundamental to our understanding of the nuclear deterrent. And because we can no longer make it like we used to, so when we have to modernize the stockpile, we're doing it differently than we were before. And so those materials challenges from aging and modernization are absolutely fundamental to stewardship.
In a small pencil beam of protons, we generate a megawatt of power.
Now what that means is by the time they come out the far end of this, which is almost half a mile down the way, they're running at about 84% the speed of light. If we could let them just go out the end of the machine and go around the Earth, they could go around the Earth almost 6 times per second.
So that's a very powerful accelerator, and you can use that to do a lot of things. Mostly what we use that for is to do radiography with those protons. Things that happen in 100 billionths of a second or a millionth of a second, we can look at how those material evolves on those very short time scales.
PRAD is short for proton radiography. It's a facility that does very fast dynamic radiography of dense dynamic materials.
So what we do here, which is important, is small experiments taking a little piece of the physics that people want to study that might go on in a nuclear weapon and build a small experiment and look at it here. So for instance, with IHE, studying the size of these dead zones.
So essentially we're probing macroscopic observables, such as a detonation front or the areal density of material as it propagates through time. And the part that's tweaked is the microscopic elements, subtle physics parameters that we can't actually see.
So the measurements we make go both into developing the science, how the phenomena work, and also into the integral big weapons code that can't really incorporate the science at that detailed level yet.
do experiments here that can tell us whether it's an aged sample or a material that you've maybe manufactured in a different way than when we first made the nuclear weapons, because we can't manufacture them the way that we used to. We take those materials, we can take them down to the Lujan Center, and we can look at their structural properties.
These weapon systems are made out of different materials that are joined together, and then when you have different materials with different properties that are joined together, they experience very different forces, and with neutron diffraction we can see these stresses and strains that develop.
The materials inside of a nuclear weapon are in an unforgiving environment, and they've been there for decades. A large part of doing our mission is understanding how the microstructure, the organization of the atoms on a microscopic scale, evolves with time and how that affects the properties and the performance of the material. So in that sense, the time evolution is the processing variable, and it affects the microstructure, and the microstructure changes the performance. With neutron diffraction, we can very accurately measure the spacing between atoms in a crystalline solid. When this component is built, hot metal is put down on a cold substrate. When that hot metal shrinks, it's constrained by that cold surface, putting a stress on the atoms in the hot metal as it cools. And the atoms in the hot part are pulled apart. Those springs that we can measure are lengthened. By measuring that length and knowing the spring constant that Peter Debye told us was there, we can calculate the force on those atoms, in other words, the stress. That number then goes into lifetime calculations of when this part might fail in an application situation.
Past measurements of the capture type could tell you, I saw a gamma ray. That's all they could tell you. This can tell you, I saw a gamma ray or a number of gamma rays, and the details of how they came out, how much energy and what numbers they were, can teach us a lot about, is this background, is this the physics we're interested, and really dive into the details of how the experiment worked. That is how we establish what we understand about our uncertainties.
We are not just stopping understanding of these elements that we actually have abundantly in the Earth. We are now going to the era that we are going to study the elements which have very short half-lives, meaning that they only exist less than a second. But they show up in all these explosive events that they exist and they disappear. If you don't provide nuclear data about those elements, then this is the ones that we just didn't explain in the past carefully. But now, with all these advances in various fields, we are going to explore those very short-lived elements.
Because of the advances in the detector systems, the electronics that go with them, that lets us take higher rates and play different games and how we get at the physics, and the brightness of the facilities themselves means the error bars both get smaller, but also more believable. And it turns out both of these things are important in order to serve the applied purpose that we're going after.
What I've been interested in the past 10, 15 years has been studying the effect of radiation on semiconductor devices. Semiconductor devices, as you know, are all over, are in everything, and the greatest threat to semiconductor devices, it turns out, comes from radiation. It turns out that the spectrum of neutrons, that is the shape of the energy spectrum of neutrons that are produced by cosmic rays, is very similar to the spectrum of neutrons that we can produce here. Modern weapon systems have a lot of semiconductor devices which have to work reliably. In fact, some of them are required to work in extreme environments, so they can be tested here and see if they meet those requirements or not.
We have the whole package, so it goes to synthesis, fabrication, manufacturing, to characterization, to theory, simulation, and modeling. It's kind of a co-design capability that is resident at the laboratory.
So being a part of a facility like this that has a very unique capability, we're continually probing in unknown physics.
In this world where we're not testing anymore, we really do want to understand that underlying physics in order to feed that data into our calculations and try to certify things without testing.
So I'm looking forward to a really long future here, and I think it's important for the laboratory. I think LANSCE is important for the country.
And in a lot of basic science, you can work on challenging problems your entire career and never actually figure out the answer. Here we take on challenging problems and we get together strong teams of people and we actually figure out the solutions to those problems, which makes it a very satisfying place to work.